Hello and welcome to another lecture for stats. This should be the last main lecture for the semester. In this lecture, we will be talking about Anova. So prior to this point, we've looked at things like one sample test, two sample tests. Well, what if you've got more than two samples? Or looking at it from a way when we did the non-parametric with chi-squared, we looked at, well, what if you've got two categorical variables? So you're comparing one categorical variable to another. And so there's a very big similarity between what that is and kind of mixing together a little bit of the one and two sample stuff to make Anova. Anova is going to be once you've got multiple samples, more than two samples, more than two groups. So we break our different samples down now into groups. So let's say we did a we were testing a painkiller treatment, and we had Tylenol, a placebo, and a new painkiller. So now we've got three groups or three categories. So that in that way it is pretty similar to chi-squared. But chi-squared was when you were looking at two categorical types of variables like that, when you had two variables with multiple groups. Anova is when you've got one variable with multiple groups, multiple levels, and you've got another variable that's a continuous variable. And the measure of what's on the different groups is also needs to be a continuous in a way measure. So this is where it goes back to one and two sample tests. When we had one sample test, we were just looking at one sample, one group, and comparing it to some hypothesized mean. With two samples, we were looking at two different groups and looking at the difference between the groups, looking at how one group compared to the other. Anova is now going to take that to three or more groups. So we're going to look at hypotheses between groups and within groups. We'll look at mean square, we'll do the F ratio, and then we will, with this, talk about a post hoc test. So when we did the non-parametrics with chi-squared, I talked about how you need to do post hoc tests and how we weren't going to cover it. But with Anova, you have to do post hoc tests as well. We are going to cover a post hoc test, and you are going to have to perform the post hoc test. Okay, so we need to answer a question before we get into this, and that is, why do we need another test, just another test in general? So in t-tests and z-tests, there's only one possible difference when we're doing a general, like let's say two sample test. So if you've got a two sample test, whether it's a t-test or a z-test, you've got sample 1 and you've got sample 2, you're checking one difference, so one difference. So your type 1 error rate is just equal to your alpha. Your alpha that you set is your type 1 error rate. We're just looking at one difference. But if we're interested in more than one, or more than two really, populations, if we're interested in more than two populations, let's say we're interested in three, then what ends up happening is there's three possible differences between pairs of means. So with three samples, you've got 1, you've got 2, and you've got 3. Well, you've got a difference there, a difference there, and a difference there. So you've got three differences. And if you had a 4 sample, it even gets into more. Then you've got 6 differences. 5 samples, you've got even more. The issue here is that our type 1 error rate changes because of this. If we did it with 3 samples, if we did it like we were doing with a t-test, where we looked at the comparison between each of the groups, well, we'd have alpha here, and alpha here. The problem is we've got 3 opportunities for a type 1 error. What ends up happening there is that increases the type 1 error. So if we conducted those separate 2 sample tests for each pair of means, with a single test having an alpha of 0.05, if we did 3 tests, our overall probability of making a type 1 error is 0.1426. You'd think it's 0.15, but if you remember the way we did probability, that if you've got, this would be the additive principle, so you do 0.05 plus 0.05 plus 0.05 minus any overlap between them. That's why it's actually 0.1426. That's arbitrary. I'm not going to ask you about that, but the point is that if we did 3 different comparisons, so instead of just doing the one comparison where we've got an alpha of 0.05, if we did 3 different comparisons because we've got 3 groups, our probability of making a type 1 error would go up to 0.1426. As when we talked about error is bad, we want to minimize error, so by upping our chances of falsely rejecting the null hypothesis from 0.05, which is about the highest we'd allow it, to 0.14, that's unacceptable from a stats perspective. So this is what's called family-wise error. So if I were to ask you a question like, why do we conduct an Anova instead of multiple pairwise comparisons or multiple two-sample comparisons? And it's because of family-wise error. Family-wise error is also called pairwise error. You might hear it called that. But family-wise error is basically that as your number of comparisons goes up, your probability of making a type 1 error goes up. So if you make 20 comparisons, your probability of making a type 1 error is going to be pretty close to 100%. So because of that, we don't do multiple comparisons like this if we've got more than 2 groups. Another approach, so the first approach would be to conduct multiple pairwise samples, pairwise comparisons. A second approach would be to actually reduce our alpha level. So if we took and did an alpha of 0.01 and had 3 comparisons, well, our overall chance of making a type 1 error is now less than 0.05. However, the problem with this is type 1 and type 2 error are inversely proportional. As you reduce your alpha, your probability of making a type 2 error goes up. So by just reducing your alpha, you're increasing your chances of making a type 2 error, failing to find an effect, failing to reject HO when you should have. At 3 comparisons, this isn't as big of a deal. You can reduce it to 0.01 and you're still pretty good. But what if you're making, like I said, 20 comparisons, 100 comparisons? At that point in time, yeah, you might reduce your alpha to 0.001 and you're controlling and you're not getting type 1 error, but you're pretty much guaranteeing that you're going to get type 2 error by doing that. So instead, the third approach is to perform an Anova. An Anova, also called an analysis of variance, is essentially looking at the variance between the different groups, is one way to compare it. The variance between within groups differences and between groups differences, and from there making one decision about the test. So this is a Omnibus F test is another way it's called. And you'll hear Anova called the F test. That's because it uses the F chart. It has an F critical. So Anova is the Omnibus F test, and it detects any differences between means between groups, but your type 1 error rate for this test is just your alpha because it's a single test. So it detects if there's any differences between groups, but it's only one test, so it only has one chance of making a type 1 error. However, just like with chi-squared, a statistically significant F test only indicates that there's a difference between means. It doesn't indicate what differences are present. So if you've got 3 groups, 1, 2, and 3, the F test is going to tell you that one of these is different. It doesn't tell you which one of them is different. It could be that all of them are different. It could be that only one of them is different. The F test just says that one of these differences, one of these 2 groups' difference is significant. if you have a mean for group 1, a mean for group 2, a mean for group 3, the mean for group 3, the F-test is just saying that one of those the differences between the means between groups, one of those that's there is significant. It's not saying, at least one, sorry. It's not saying which one is. To determine which one is significant, you have to do a follow-up test, or what's called a post hoc test. So post hoc tests are tests that you do after you've already done your normal test, and they detect which differences are significant. We are going to do what's called a Tukey's HSD post hoc test. There is many different post hoc tests that are out there. We talked a little bit about them with the chi-squared test. There is a dozen at least post hoc tests for the F-test. So we're just doing one of the many, and that we are going to do Tukey's HSD is what it's called. Okay, so let's look at just an overview first of what is ANOVA. So, and when can it be conducted? So first of all, it can be conducted with any number of independent variables. Each level of the independent variable needs to consist of 2 or more levels. Typically, when we're talking about this, we're talking about having 3 levels. Because if your independent variable only has 2 levels and you only have one independent variable, then you don't do an ANOVA, you just do a 2 samples test, because you've only got 2 levels. So when we're looking at, typically we're talking about independent variables that have more than 2 levels. However, because you can have more than one independent variable, if you've got more than one independent variable, let's say you've got 2 independent variables, they could each have 2 levels, but now you've got multiple different groups in a sense, because you've got a group that has the first level. So I think I got some space here. Let's say you've got IV1, independent variable 1, that has 2 levels, 1 and 2. And then you've got IV2 that has 2 levels, 1 and 2. Well, the issue is that you're going to have now 4 groups. You're going to have 1, 1, so somebody who is 1 on independent variable 1 and 1 on 2. You're going to have 1, 2, somebody who's 1 on 1 and 2 on 2. You're going to have 2, 1 and 2, 2. So you're going to have 4 different groups, so you're not making just one comparison here. So in this sense, you could have independent variables with only 2 levels, but if you've got multiple independent variables, you're then making more than one comparison. An ANOVA that assesses only a single independent variable is called a one-factor or one-way ANOVA. So example is determining if teaching method has an effect on student performance. So student performance is our interval ratio level dependent variable. It is the measured variable. It is our outcome variable. However, we're interested in seeing if 3 different teaching methods, if there's a difference between them. So we've got traditional, collaborative, and coaching teaching method. So our independent variable has 3 levels. So in a sense, now we're going to have 3 groups. One group or one sample is the traditional, another group is the collaborative, another group is the coaching. So we are making multiple comparisons, 3 comparisons, because we've got 3 different groups. This is what's called, again, a one-way ANOVA. For the purposes of this class, we are going to just be doing one-way ANOVA. There's other times where we could do 2-way, but for this semester, I'm just doing one-way ANOVA. So an ANOVA that assesses the effects of 2 independent variables is called 2-factor or 2-way ANOVA. For example, if we were determining if teaching method and time of day have an effect on students' performance. So we've still got that same measure of student performance. We've actually still got the same first independent variable, but now we're looking at time of day as well. So we've got another independent variable. So we've actually now got 6 groups that we're making comparisons between. So we've got traditional morning, traditional afternoon, then we've got collaborative, collaborative in the morning and afternoon, and coaching in the morning and afternoon. So we've got 6 different groups. So we are making many different comparisons. We're comparing these two, we're comparing these two, these. So that's 1, 2, 3, 4, 5 comparisons, but then we're also comparing here 6, 7, 8, 9 comparisons, 10, 11, 12 comparisons, 13, 14, 15 comparisons, 15 comparisons total. So if we were just doing these as 2 sample tests, we'd have 15 chances of making a type 1 error at 0.05. But because we're doing this as an ANOVA, we would do it as just 1 comparison. So ANOVA can be extended to any number of independent variables. Again, this is a 2-way. We talked about a 1-way on the previous slide. You could do a 3-way, 3-factor, as many as you want. We're going to only focus in here on 1 independent variable, though, just because adding more doesn't change too much. It just adds basically, adding more independent variables just adds 1 more level of analysis to our ANOVA, so there isn't that much difference to it. So if you get the basics of ANOVA down, you've got the basics of 2-factor. Alright, there's another way you can do ANOVA. Just like when we did 2 samples, you can have independent or paired samples. So independent is when you've got 2 different non-correlated groups. Correlated or paired samples is when you've got within subjects or repeated measures, or you've got another pairing mechanism. It gets harder and harder when you've got more than 2 groups to have a pairing mechanism that isn't a within groups measure. So repeated design where you, let's say we were doing our painkiller, you do the placebo 1 week, Tylenol the next week, and our new painkiller the 3rd week on the same people. You can do it either way, just like with 2 sample tests, where you had independent and paired, you can do that with ANOVA. However, for in here, we're just going to look at independent samples. We are not going to look at repeated measures. Like I said, it's possible to do it that way. It's a slightly different analysis. The formula is different, but at the same time, we're not going to cover that. We're just going to cover independent samples. I talked about earlier the assumptions of different tests and how I was going to give you some. Well, the assumptions for the ANOVA is, first off, that you've got a normal distribution, and this is a normal distribution for all variables. So all levels of the independent variable have to be normally distributed. Homogeneity of variance is a assumption of ANOVA, and what that means is the variance between the different groups has to be the same. So if you've got 3 different levels, each level's variance needs to be the same. Independence of observations, that's pretty obvious. Interval or ratio level DV, that's again a parametric assumption by default. Going back to the normal distribution, of course, you can use the central limit theorem on this one. So if your sample size is sufficiently large, you can ignore this. So normal distribution or sufficiently large sample size. Our hypotheses, this you're going to see is pretty similar to the chi-square hypotheses, but now we're using means. There's a couple different ways to say this. One is that for the alternate hypothesis is that mean 1 in a sense doesn't equal mean 2, doesn't equal mean 3, doesn't equal mean 4. And you see here where I say for sum of I is not equal to j. Basically what that's saying is that at least one mean is not equal. And that's where you get this down here. You can just write it out easier for your alternate hypothesis. At least one of the means is not equal, because not all groups have to be significantly different for the f-test to find significant results, as I've already talked about. However, the null hypothesis is pretty much the same. That is that all means are equal, all groups are equal. So mean 1, in another way to write this, let's say you've got 3 groups, For the null would be mean 1 equals mean 2 equals mean 3, and for the alternate at least 1 mean not equal. So that would be how you'd write it if there was 3 means. If there was 4 means, you could add a 4th mean on there. You could also, for the alternate again, put at least 1. Another way to write it here would be at least 1 mean 1 not equal to mean 2 not equal to mean 3. So that would be another way to write it. There's multiple different ways to write it. I just prefer saying at least 1 mean is not equal. That's just the easiest and simplest way to do it, but however you choose to do it, as long as you're getting the point across that the null hypothesis is that all means are equal. The alternate is that at least one of the means is not equal to the others. Here's the next part of ANOVA. When we're doing ANOVA, we're going to use a source table. So a source table is basically a table that lists all the relevant information. If you use a statistics package like Excel or SPSS or any of the other ones, SAS-R, they will give you the ANOVA table when you perform an ANOVA, when you conduct an ANOVA. And an ANOVA table is basically going to have these pieces of information. And this is a one-way ANOVA table. If you've got a two-way ANOVA table, it's basically going to add one more level right here. So there'd be just basically one more row. But the columns stay essentially the same. It just add one more row. But since we're doing one-way ANOVA, you get the simpler table. What we're going to look at here is we're going to have within and between, and then total. We're also going to have sum of squares, that's CSS, sum of squares, degrees of freedom, mean square, and then our final F value. And as we're doing all the different formulas, and that's the one thing that makes ANOVA the most complicated thing we'll do, is that there's multiple different formulas you do along the way. But as we do these different formulas, we will fill in these different boxes. And in the example, you'll see, and even in when I'm giving formulas, I'll fill in these boxes as we go. Let's start with sum of squares. So this is why last week when I was talking about regression, I included, so when I was including regression, I used basically sum of squares regression and sum of squares residual. That ends up being essentially the same thing as sum of squares between and sum of squares within when you're looking at this, meaning that you have it's partitioned between, within, and between. How does that make sense, or what is going on here? Well, what we're doing here, and I'll talk about this again when we get to the mean square, but what we're interested in here is the differences within groups and the differences between groups. So within and between. Let's say we've got 3 groups. Any differences that we find within a group is, in a sense, error. So that's going to be our within. That is error. Why is that error? Why is within differences error? Because any differences you have, let's say I collected a sample of 20 people for, and I've got, let's say I've got the 3 different drugs again. I've got 20 people in the placebo, 20 people in the Tylenol, and 20 people in the new drug. Any differences I find between people within each of those groups. So if the 20 people that are in the placebo group, any differences there are essentially error, because that's not differences due to my treatment, that's differences just due to differences in the population, differences in people. So that is error. So we are not interested in that. We still have to calculate it, but we're not interested in it. What we're interested in is the differences between, because that's our effect. Our effect is the differences we find between. So any differences we find between the placebo group and the Tylenol group and the placebo group and our new group, that is an effect. There's an effect there. What we would like is our effect to be larger than our error, because that means there's actually an effect. If the differences between groups is smaller than your differences within groups, then you really don't have a difference. That's just a artifact of error. So we want our effect differences, or our differences between, to be greater than our differences within. Like I said, I'll come back to that, but I wanted to preface it here to kind of get you into the mentality of, well, what is between and what is within. So we're going to partition our sum of squares. And sum of squares is calculated in a very similar way to what we did for two groups. Sum of squares is basically a way to calculate variance when it's the first step to calculating variance. Why is it the first step to calculating variance? The same way when we first talked about it at the beginning of the semester, very early on, like the third week of the semester. You can't just calculate out an average difference from the mean, because then it gets to 0. So we do sum of squares as a result. Our sum of squares, though, we're going to have 3 different sum of squares. We're going to have our sum of squares total, which is our total variance, and this is between and within all groups. So our sum of squares total is just going to be, you put everybody together into one big group, and that is our sum of squares total. However, then we partition that into our sum of squares between and our sum of squares within. So our sum of squares within, again, is error. Our sum of squares between is our effect. We also do degrees of freedom. Degrees of freedom is partitioned in the same way. You've got your degrees of freedom total, that's with everyone together. You've got your degrees of freedom between, that's the degrees of freedom between groups, and your degrees of freedom within groups. When you're doing ANOVA, you need both of these degrees of freedom between and degrees of freedom within when you go to the chart to get your F critical, but we will come back to that. So if we're looking at the first step to our source table, we've got just some formulas we can plug in. We can't get to the end yet. These aren't our final formulas, but we can look at this. So our degrees of freedom total down here at the bottom, if we look here, is equal to the degrees of freedom between plus degrees of freedom within. Well, from that, just simple algebra gets you to degrees of freedom between equals total minus within, and degrees of freedom within equals total minus between. Same with sum of squares. So sum of squares total equals sum of squares between plus within. Simple algebra tells us that sum of squares total minus within will give you between. Sum of squares total minus between will give you within. What the advantage actually to this is, to understanding this, is that you'll find that you actually only need to calculate 2 of the 3 sum of squares. Degrees of freedom is easy to calculate, so that won't be a big deal. But sum of squares is more complicated to calculate. Because you've got these simple formulas, you can take, as long as you've got 2 of your sum of squares, you can find the third one. I still recommend calculating out the third one by hand while you're doing this on the homework and the exam, because that'll be a way to double check. If you calculate, let's say you've got the within and between, you add them together to get the total, so you didn't have to calculate out the total. But if you go and calculate out the total by hand and it gets the same answer as your between and within, then you know you did it correct. Okay, let's look at some of these formulas. Looks like the timing's a little bit off on this, but let's look at, so sum of squares total equals the sum of xt squared. So that's going to be the sum, and when the xt there is x total. This is going to be everybody in your study. So if you've got 60 participants, 20 in each group, it's going to be all 60, their x value squared added together. And then each x value, all of those summed, squared, divided by your nt, big thing there, that the T again is total. That's going to be everyone. And you'll also see that the N here is capitalized to differentiate it from the different sample means. This is your total N. Your sum of squares between, though, is now a little bit different. Your sum of squares between, you need to take each group and do them separately. So you first need to do the sum of all of your x's from sample 1. Square that and divide that by your n for sample 1. So in this case, your n for sample 1, and in my example I've been giving with the drugs, would be 20 because there's 20 in group 1. But you would add up all the x's for group 1, square that, and divide by n. Then you do it for group 2, then you do it for group 3, then if you've got a group 4, group 5, all the way to k. K just here means that you go to the end. You do it for every single group you have. If you've got 5 groups, you do it for all 5. If you've got 3 groups, you only do it for those 3. Then you need to subtract what you got from above, or the second half of what you got from above, sorry. So when you look up here, it's the same, so you only need to end up calculating that once. You don't subtract your sum of squares total, but you do subtract that sum of x total squared divided by n total. So that's your sum of squares between. Sum of squares within is kind of a little bit easier because it's the standard sum of squares formula we've been doing, but it's the sum of squares formula for all of the different groups added together. So the sum of squares for group 1, sum of squares for group 2, sum of squares for group 3, sum of squares for group 4, all the way up to all of the sum of squares. So again, the K here just means do it for all groups. So that's our standard formula. Group 1, we've got the sum of x's for group 1 squared minus the sum of x's for group 1, and then that value squared divided by n1, and then that's the sum of squares formula for group 1. That's the same sum of squares formula we've been using for this point. Then you do that for group 2, group 3, again all the way to the end. So I'll leave it up to you which formulas you find are the easiest, how you want to do it. If you want to calculate all 3, that's the way, again, I recommend it. But like I said before, you only need to calculate 2 of the 3 of these because you can get the third one from those 2. Let's plug these into our source table. It gets a little bit smaller with our source table here, but I did want to put them all in one place. So you can see here, the sum of squares within, I didn't put the full formula because you should know the sum of squares formula by now, or you can get it in other places. It's just the sum of squares total formula with the different groups instead of total. So I didn't put it all here just to save some space. But now you've got it a little bit easier here. You've got all of these in one place. However, now we've calculated out the sum of squares. Now we need to figure out degrees of freedom, mean square, and f. So the hardest part is actually done. Calculating out the sum of squares, the 3 different sum of squares, the sum of squares total, sum of squares between, and sum of squares within is the hardest part. But once you're done with this, you still have a little bit of work to do, but you're done with the hardest part. The next, we're going to look at mean square. And we'll look at degrees of freedom here as well. But mean square is basically where we are going to turn those sum of squares with degrees of freedom into variance estimates. So if you remember back to, well, what was our variance estimate when we looked at 2 samples? We just took our sum of squares and divided by our degrees of freedom, n minus 1 in that case. So in those cases, it was pretty easy to do. Degrees of freedom, or sorry, sum of squares divided by degrees of freedom is our variance estimate. Well, now that we've got multiple different groups, multiple different comparisons that are going on, we're actually going to get 2 variance estimates. We're going to get a variance estimate between groups and a variance estimate within groups. Variance estimates, they're also sometimes called mean square or mean square estimates. So you hear me calling them variance estimates, but the stats term for them is mean squares. So these are going to be two different variance estimates that we're going to be looking at. So mean square between is based on the differences between or across groups. So mean squares between, it's equal to our sum of squares between divided by our degrees of freedom between. And here you actually see the formula for degrees of freedom between. Degrees of freedom between is k minus 1, where k is our number of groups. So if you've got 3 groups, as in the example I keep giving with the placebo, the Tylenol, and the painkiller, 3 groups, 3 minus 1 is 2. So our degrees of freedom between is just number of groups minus 1, or in this case 2. So you take that sum of squares between that you calculated and divide by k minus 1 to get our mean square between. As I said, the hardest part of Anova is calculating the sum of squares. These are just very simple steps now you just have to do to convert those sum of squares into our final form. Mean squares within is based on differences of within groups. And again, this is error. So mean square within is also called mean square error. Another way to say mean square within is MSE, or mean square error. So this is the differences within groups. So it's equal to the sum of squares within divided by the degrees of freedom within. And our degrees of freedom within is equal to our n, and this is the big N. So this is our n total minus k. So our total n. So if in our example that we've been using where I had 20 participants in each of 3 groups, we've got an n total of 60. 60 minus our number of groups, which was 3, 60 minus 3, so in this case our degrees of freedom within is 57. So you take your sum of squares within and divide by your degrees of freedom within. And let me actually bring up the next part. So since everyone in a group receives the same treatment, any differences in scores within groups cannot be explained, and it's considered error. Thus, mean square within, or MSE, is considered pure error. And our degrees of freedom, you see the different formulas. Degrees of freedom between is k minus 1. Degrees of freedom within is n minus k. Again, degrees of freedom total is just degrees of freedom between plus within. That's one way to do it. Or you can take degrees of freedom total and do n total minus 1. So in the example that I've been using, where n total is 60, our degrees of freedom total is going to be 59. If you look at that, so our degrees of freedom within I talked about was 57. Our degrees of freedom between was 3 minus 1, or 2. So that's 57 and 2. You add those together, you get 59. You get the exact same answer as if you did n minus 1. So let's plug all of this now into the Anova table before we get to the final step, and the final step is easy, but now we've included our different degrees of freedom formulas here and our mean square formulas. And again, our mean square formulas is just the sum of squares divided by the degrees of freedom respective for between and within. So I told you I'd talk about this error stuff and why or how this comes in and between and within, and this is where I'm going to talk about that. So in general, we want between group variances to be high. If there's variability between groups, that means there's big differences between groups. As a researcher, we're typically trying to see between group differences. So in this case, we want there to be high between group differences. However, we want within group differences to be low because within group differences is error. It's error we can't control, but it's error that we can account for. So because we can't control it, it's going to be there. However, we want it to be as low as possible. And looking down here, the worst case scenario is on the left. Worst case scenario is when you've got each group has a lot of variance between. So we've got 5, 7, and 9, but lots of variance within. So there's lots of variance within each group, 5, 7, and 9. However, there is no differences between groups. All of the mean for all three of these groups is going to be 7. So our between groups variance is nothing, and our within groups variance is present. In our best case scenario, there is absolutely no within group difference. So A is all 5s, B is all 7s, C is all 9s. But there is difference between each group. So our between groups differences is present, but there's no within group difference. You're never going to get that. You're going to get stuff between, but the point, somewhere between our worst case and our best case. But the point is we want our between group differences to be higher than our within group differences. So you can kind of get to what we're going to do with F here, because F is a ratio. F is a ratio of our between group differences to our within group differences. And the higher our F value, the larger the ratio is to our between to our within. Let's look at that then. So a ratio of between group variance, mean squares between, and our within groups variance, or mean square error, mean square within, is obtained. And we put our mean square between over our mean square within. So if our mean square between is greater than our mean square within, our F is going to be greater than 1. If they're equal, our F is going to be 1. As F gets larger and larger and larger, then our basically our ratio of our differences of between group variance to within group variance is larger and larger and larger, meaning there is more between groups than there is within groups variance. Our F is always going to be positive. Our F critical is always going to be positive. And just like chi-square, our hypotheses are always two-tailed, non-directional. So in this way, just like we looked at with chi-square, we want our F value to be as big as possible, because the bigger our F value, it basically means there's more between group differences than there is within group differences. Our differences that we're finding due to an effect is greater than our differences due to error. I hope that makes sense. So when we plug in that very simple formula here at the end, mean square between divided by mean square error. So again, like I said before, the hardest part of all of this is the sum of squares, calculating out those three sum of squares. Degrees of freedom are pretty easy to calculate. Mean square, once you've calculated sum of squares, easy. They're just ratios. And then F is another ratio. So once you've calculated out sum of squares, it's just step by step to get to the final answer. And this is where you've got all of the source table in one place with the formulas. Anytime after this, when you see the source table, it'll actually have values in it and examples. It won't have the formulas in it. So this is your and I'll put this in the study guide too for the final, but this is your one stop for all of the formulas for sum of square, for Anova. This is the F critical table. I'm sorry that it's not that great of a table. You can get it online too. You can actually put in, there's calculators too that you can just put in, F critical calculators. But for this, you need a couple pieces of information. You need your degrees of freedom for the numerator. That's your degrees of freedom between. Your degrees of freedom for the denominator. That's your degrees of freedom within. Across the top is your degrees of freedom between. Goes that way. Degrees of freedom within goes this way. Your degrees of freedom within is generally going to be much higher than your degrees of freedom between. That's why you see the degrees of freedom between going only over to 21. And typically for in here, you're only going to actually use up to 3, maybe 6. Not that much. But your degrees of freedom within, that's going to be your n total minus your number of groups. So it can go up there. Just like when you did the t-test, always round down if your degrees of freedom is between two of these numbers you see down at the bottom. It goes 40, 48, 60, 80, 120, 240. Always round down there. That being said, and this is by the way, this is the alpha of 0.05 chart. If you've got a different alpha, you have to do an entirely different chart. But because it's always non-directional, you only have to worry about one chart for each alpha. Just like chi-squared and just like t and all that, if your observed is greater than your critical, you reject HO. If your observed is less than your critical, you fail to reject HO. So greater than or equal to, you reject. Less than, you fail to reject. So let's say you've rejected. Now, after you've rejected, you need to do a post hoc test. Post hoc tests, and as I said before, are just a test now to find where the differences are present. And as I said before, there's many tests you can do, and here we're going to do Tukey's HSD. So rejecting the null just means there's a difference between groups. We conduct the post hoc to determine which differences are present. We're going to do Tukey's HSD, which is also called Tukey's honestly significant differences. And it's anytime you've got a difference between two means that's greater than our HSD, then that's considered statistically significant. So our HSD is going to be something that's going to be based on, is in a sense, a cutoff level of difference between two means. Any means that are greater than that become significant. So this is our Tukey's HSD critical chart, because the Tukey's HSD test, as you see here, the HSD is going to equal Q critical times the square root of our mean square within divided by n. And you notice this is a lowercase n. Because this is a lowercase n, this is sample n, one sample n. So this is the different samples. So first off, to use Tukey's HSD, all of your samples need to have the same n. So all of your samples need to have the same sample size. You can do Anova with different samples with different sample size. The examples I've been giving where you've got 20 in each, that is where you've got the same. Everything we're going to do in here is always going to have n's with the same sample size. However, you can do Anova with different sample sizes for the different categories, the different groups. But again, for in here, we're just going to do it with the same. So you can do in Tukey's HSD. So this is the one sample. So in this case, it would be, in our example we've been using, the n here would be 20 because it's the n for one sample. To get Q critical, you need the K, which is the number of groups, you need alpha, and you need your degrees of freedom within. K is across the top, the number of groups, degrees of freedom within is along the side, and this is the alpha for 0.05, again, the one we're going to be using as a default in here. And then you've got, of course, n is the number of scores per group, and mean square within is your within group's mean square. So this is how you would calculate the HSD, and from there you would compare each of the mean differences. So you'd take the mean for each group, you'd take the difference between each of the means, any of those differences that are greater than your HSD you reject. Let's actually use an example. I'm going to go through this example relatively quick, but let's use an example. So the example we're going to use here, so you get to see all of this in action, is assume we want to compare the effectiveness of 3 different drugs on memory. We've got drug 1, drug 2, and drug 3. We've got 3 different subjects in each group. So our N1 is equal to 3, our N2 is equal to 3, our N3 is equal to 3, and our N total is equal to 9. We've actually got all the other information we need here beyond that, except the fact that we needed to put some N's. We don't have our means here either, but if you took our means, so we could just look at this real quick since it's an easy divide by 3. Mean 1 is equal to 60 divided by 3, or 20. mean 2 is equal to 135 divided by 3, or what is this going to be? 33, 43, 40. I should know that quicker. I'll come back to that. My mind just stopped for a second. Mean 3 is easy. It's 33.33. But 135 is going to be, it's 45. I don't know why it took me so long to get to that. So our mean's going to be 45 there. I could have just looked at it and seen that that's 30, 45, and 60 and gotten to that quicker. That took me way longer than it should have. But now we actually have all the information we need to do the tests. You would need to also do, so when I said we have all the information, so no, we don't. Our X total would have to be 60 plus 135 plus 100. So we've got 235, 295. And our X total squared is going to have to be 1400 plus 6525 plus 3400, and that equals, what is it, 11,325. So now, I'm correcting myself for the third time, now we have everything we need to conduct the ANOVA. We have the x's and the x squareds for the individual groups. We have the x and the x total, the x squared for the total. We've got the n's for each group. We've got the n total. We've got our means. K equals 3. That's not a piece of information we needed at this point, but k equals 3 because k is the number of groups. So let's actually start factoring this out. So first is sum of squares total. Sum of squares total is going to be that 11,325 from the previous minus the 295 squared divided by our n total, which is 9, or 1655.56. Next is our sum of squares between, and this is just where you take in each group, you do the x total, or the x for the group squared divided by the n for the group. That's what's here, here, and here. Then you take that, again, that total, the x total squared divided by the n total, and we get 938.89. Now to do the degrees of freedom within, we could just do 1655 minus 1655.56 minus 938.89, but let's actually calculate it out. So if we calculated it out, you do the sum of squares for each group. So sum of squares for 1 is 1400 minus 60 squared divided by 3. You add that for the sum of squares for 2, the sum of squares for 3. Add them together and you get 716.67. And again, you can double check yourself. Do this 716 plus 6.67 plus 938.89. You add those together and you get 1655.56. So it actually comes out to correct. Degrees of freedom become pretty easy. Degrees of freedom between is k minus 1. K was 3, so 3 minus 1 is 2. Degrees of freedom within is n minus k. Our n total was 9 minus k, which was 3, is 6. Add those together to get 8, or take n total, which is 9 minus 1. Now we get our mean square between by taking that 938.89, dividing by 2. We get our 469.44. To get our mean square within, we take the 716.67, divide by 6, and we get 119.44. And then to get our f, we take the 469.44 divided by 119.44, and we get a 3.93. So our f test, our f ratio is 3.93. Now that we've done that, we would need to do a post hoc test. but that is the basics of the example. Let's now do another example, but this time we're going to do it with a post hoc test. So Nate wants to know if type of job is an indicator of how tough a person is. Selects 15 participants, subjects them to increasingly severe electric shocks while measuring the time it takes for them to scream out in pain, measured in seconds. This would be unethical. Actually, what would probably be done here is there's an ethical way to do this test. That would be there's a ice tank. It's a tank of water that you keep at a constant cold temperature, and you have people put their hand in it, and the amount of time you can keep your hand in it, because it's a painful thing to do, the amount of time you can keep your hand in it is a measure of how basically your pain tolerance. So giving shocks, not ethical. Having people put their hands in ice water, ethical. So they want to know if there's a significant difference between the groups using an alpha of 0.05. And here are the amount of seconds that each person could last. Administrators, very short. Clowns in the middle. Football players, a little bit higher. So our null and alternative hypothesis here is that there is no effect on of type of job on toughness. The alternate is that there is an effect. Another way to write the null here would be mean of clowns is equal to mean of football players is equal to the mean of administrators. And then the alternate would be at least one mean is not equal. At least one of the means is not equal. We're doing an Anova because there's 3 means. It's two-tailed because Anova is always two-tailed. Our alpha here is 0.05. Our n's, now you're starting to see that we need more information here. The n, you can just write the n as total as 15. You can also, including to that, write n1 equals 5, n2 equals 5, and n3 equals 5. So you can put that in addition. If you just have the n total, that is fine. I prefer if you write the different group n's, but if you just have the n total, that's fine. However, degrees of freedom, you have to put all 3 in step 4. Degrees of freedom total is n total minus 1. Our n total is 15, so it's 14. Degrees of freedom between is the number of groups minus 1. There's 3 groups, so it's 2. Degrees of freedom within is either going to be degrees of freedom total minus between, 14 minus 2 equals 12, or it's our n total minus our number of groups. Our n total is 15, groups is 3, so that's 12 as well. Need to do a little bit of math here. The little bit of math gets us to this point. And again, we've got some means here. You can also do x total. It's going to be equal to 40 plus 60 plus 16, so 116. You can do the x squared total, which is 730 plus 326 plus 54, which ends up coming out to, what is it, 1,110. Our n1 equals 5, n2 equals 5, n3 equals 5, and total equals 15. K equals 3. I think we got all the information we need here now. Let's plug these into the formulas. So sum of squares total, sum of squares between, and sum of squares within is our formulas. Sum of squares total, plug it in and you get 212. Sum of squares between, plug it in, you get 194. Sum of squares within, plug it in and you get 18.8. Mean square between, we plug it in, get 97. Mean square within, plug it in, get 157. So our F ratio, 97 divided by 1.567 is 61.94. Let's plug all of that into our Anova table. Looks like my timing is getting a little off here, but that's fine. Our F observed is 61.94. Our F critical, we take it from the chart we had earlier, and we get a F critical of 3.88. So if you're looking here, we do our various different, and let me just confirm real quick, 2 and 12, and it looks like I might need to change that chart you've got there, but that's fine. I'll change the chart and you won't even notice I changed it, except if you're listening to this, you'll notice I changed it, because that chart looks like it's off. Either that or this number's off. I'll change one of them and I'll fix it. So you see here on the right, there's a little star next to the 61.94. That star just means that it's significant. You put that star there to indicate that it's significant. And then we get step 8 here, given an alpha of 0.05 and a F with degrees of freedom of 2, 12. So you put both degrees of freedom there, equals 61.94. Reject HO and conclude that at least one group is significantly different than the others. However, we cannot complete the rest of step 8 yet. Step 8 is incomplete at this point. Because we know there's at least one difference, we don't know which means are different. We need to now do our post hoc test, and we will come back and revise step 8 with the post hoc analysis results. And this is how you do the post hoc analysis. Doing the post hoc analysis here, first you compute your Tukey's HSD. So in our example, alpha was 0.05, degrees of freedom within was 12. Our mean square within was 1.567, n is 5 because this is again n per group. K is 3. So if you look back at the chart, you look at your K of 3, your degrees of freedom within of 12, and you should get a Q critical of something like 3.77. Depends on your Q critical chart. It looks like the Q critical chart I gave you guys has a 3.204 there. So again, I'll change it here so it lines up with that chart. So if we plug all that in, we get our Q critical times our square root of mean square within divided by n. We get a HSD of 2.11. What does that HSD mean? That HSD of 2.11 means any differences between two means. So if you've got the three groups, you've got the three groups here were clowns, football player, and administrator, and you're going to look at the mean differences here. Any differences present that are greater than, any mean differences that are greater than 2.11 are significant differences, so we'll report them that way. So now we need to compute the difference between means for each one. So here we've got the mean for clowns is 8, the mean for football players is 12, and the mean for administrators is 3.2. And if you take and look at the difference between football players and clowns, it's 4. Administrators and clowns is 4.8, and administrators and football players is 8.8. You notice that there's stars next to these. You should write the chart out like this, and any differences you find, put a star next to. That means any differences you find that are greater than the HSD, you put a star next to. Our HSD from the previous was 2.12. All of these differences are greater than the HSD, so we put a star next to them. So we find that all of the differences are statistically significant. Any difference between a mean that's greater than or equal to the HSD are considered statistically significant. Since our HSD was 2.12, all of these differences are greater than that. All of these differences are significant. So all mean differences are statistically significant at 0.05. This gets us to our revised step 8. Our revised step 8 is now fully written out, given an alpha of 0.05 and an F with degrees of freedom of 2, 12. So 2 for the between, 12 for within, equals 61.94. So our F is 61.94. We reject HO and conclude that at least one group is significantly different than the others. Tukey's HSD post-hoc analysis, so you say which test you did here, which is Tukey's HSD. Tukey's HSD post-hoc analysis revealed that football players withstood the shocks for significantly longer than clowns or administrators, and clowns withstood the shocks for significantly longer than administrators. Because all of the differences were significant, you can stop at this point. However, what would you do if one of the differences wasn't significant? You would list all of the significant differences found, then you would say after that, no other significant differences were found. So let's say clowns and administrators were not different, significantly different. You would just say that football players withstood shocks significantly longer than clowns and administrators, and then no other significant differences were present. That would be how you would do that if there are some that are different and some that are not. In this case, all were different, so you can stop at the point of just reporting the differences. Okay, that is Anova. These slides ended up a little bit longer than I'd intended. Anova is pretty complex. That is just one test that we did this week, and the follow-up, obviously, the post-hoc. But that is Anova. With that, we are done with lectures for the semester. All you have to do is finish up the homeworks and the final, and then you'll be done. I'll have the review up later this week so that you have that. Remember that the homework is due earlier than normal this week because of the last day of the semester. Thanks.